muy útiles como aprender el lenguaje de programación COBOL, que no vale para nada. Entre otras cosas. Well, anyway, I will let you start talking. So the talk is actually going to be on one side. So I cannot be on TV.
Just go on.
Come on.
Maybe you will appear. Problem is that your presentation will not appear. We have two screens, so you will be there, but not the.
I'm so disappointed. Anyway, so maybe we can switch some of the lights. Maybe this one, because some of the figures are going to be. Okay. So the talk is going to be. It's going to have a lot of biology, but I don't want you to be scared. So please interrupt me at any point. Hopefully there is a pen here so I can explain more things in case you need it. But there is a mixture between what is biology and what physics can do for biology. Many times when physicists try to do biology, they try to do this the spherical cow approximation. I'm not going to do that. I'm trying to be as close to the biological problem as possible. I choose this first slide in order to introduce you the biological problem. And this is just the problem of inflating a balloon. Suppose that you have a balloon and you want to inflate that balloon. And there is a particular region in that balloon, this one, that has been marked with a different color. When you inflate the balloon, hopefully you will get a situation that is something like this. Okay? So far so good. Now suppose that when you inflate the balloon, what you get is something like that. Now the question is, what would have to happen with the balloon in order to get that final result? The first thing that you may think is that the elasticity of that particular region of the balloon is different to the elasticity of the other parts of the balloon. That's why you can get a different scaling when you get this process of inflating problem. This stupid and simple approach is actually very important in developmental biology, because when you have an organism that is growing, you have tissues that have to scale and have to grow, but some parts of the tissue and some parts of the cells have to scale differently than others. Of course, in a real tissue, this is much more complicated than in the balloon, because here you are talking about a continuous medium. But in a biological tissue, what you have is individual cells, and those cells can move one to respect to the other. So the thing is that we are going to try to understand this particular sample in a real biological context, and this is what I'm going to talk about. So the title of the talk is Puzzling Out the Mechanical Stability of the DB Organizer, and what I'm going to show you is what is a DB and what DB means. DB means dorsal and ventral, and that is a particular region in a tissue, actually when you have the Drosophila fly, there is some particular group of cells that are called the imaginal disc, and those imaginal discs will create in the future the adult organisms. For instance, there is one imaginal disc that will create the wing of the fly. All the cells of that particular group of cells are committed to create the wing, and that's it. That is very simple, because you can identify all of those cells, whether the trajectory is what I'm going to do, and things like that. So it's very well identified. And in that particular group of cells, there is a region that is called the dorsal-ventral organizer, the DB organizer. And as you will see, that particular region is committed to keep segregated to different group of cells that are the so-called compartments. I will explain in more detail everything. The important thing, as you will see, is that the DB organizer scales, when it's growing, that tissue scales differently than the other parts of the tissue. And we want to understand how are those mechanical constraints that are actually forcing that region to scale differently and to get these cells segregated differently. Oh no. Okay. Not working. Sorry about that. Okay. So here's the thing. In developmental biology, what you have is what is called boundaries in development, because there are many regions that are called boundaries that were identified like 40 years ago. And those boundaries were identified because when you have a tissue that is growing, normally what you see, if you mark all those cells, is as the tissue is growing, they start to intermingle, one versus another. But it was discovered 40 years ago that some group of cells, when they are marked, they have a configuration like that. There are a particular boundary that is never trespassed. Okay? So that is called a boundary between different cell populations, and in those cell populations normally are called compartments. The thing is that why this situation is important is because not only it can organize the tissue in different ways, and these cells are going to be committed to one thing and those cells are going to be committed to another thing, but because in this particular, this is other example about how those cells do not intermingle, but those regions at the boundary is specifically interesting not only because it doesn't allow the crossing between different regions, but also because there is a particular population that is specified near the boundary that is called the organizer, and this organizer is important because some particular proteins are secreted from them. These are the so-called morphogens, and those morphogens are actually proteins that are diffusing and they create a gradient, and the cells that are in the compartments know their position in a particular region because they can read the gradient. Okay? So that is important for providing positional information to cells. It's like creating a coordinate system in order to provide that information to the cells. So those are important for different regions. Where compartments appear? Actually, in many, most systems in biology that are committed to developmental processes. This image here corresponds to the so-called Imaginal disc. This is the group of cells that I was talking about at the very beginning. This group of cells is a bidimensional sheet, and this bidimensional sheet at the end of development will create the adult wing of the organism, of the Drosophila. Okay? There is one particular boundary that is this one that is called the AP boundary, and it's called the AP boundary because this is the anterior and the posterior boundary, and those letters are given because those cells will create what is called the anterior part of the wing, and this is going to create the posterior part of the wing. And similarly, the dorsal and ventral compartments, or the DV organizer, this part will create one part of the wing blade, and this population will create just the other part of the wing blade. Okay? Here in these examples you have boundaries and you have organizers, that in the segmentation of the Drosophila embryo you also have these kind of populations. Also in development in other systems, like in the segmentation of the so-called rhombomer segmentation that we create at the end, different can I say this in English? If you want, the rhombomeres are the ones that are specified between the different vertebrae. I don't know the word. Vertebrae. So you may think that this is a particular clone that is only interesting. Well, who cares about the Drosophila? And this is actually what Sarah Pelin said some years ago. But actually, this problem is not because it's the Drosophila. It is important because this particular problem about the dorsal-ventral compartment formation is actually the same regulatory network and the same problem that appears in vertebrate development. So it's something that is not specific of Drosophila. The same game applied in higher organisms. How is this system working? So there are different things, different mechanisms that are important here, and one of them is what is called the selector gene. I'm going to talk very briefly about that. Also the short rate signaling, because cells that are in contact, they interchange information between receptor and ligands and things like that. And also there is information that is provided in order to do that task by long range signaling, and these are the morphogens that I was talking about. There is some details that are particular about the DB organizer. I'm not going to enter into detail, but what I was most interested in is, as I told at the beginning, when you want to understand this problem, you have to consider the growth of this epithelium. So you have to consider that this particular cell's region increases in 100-fold for creating the adult wing organism. How this boundary and how this organizer deals with all these different, the division of the different cells, the movement that they can have, the different mechanisms that they have, in order to prevent this particular region to be always so well specified. And actually it's very important, because that region, the DB organizer that I'm going to talk about, is the one that is going to be the blade of the wing. So it's a very well defined border in the adult organism, and you have to keep that to be very precise. In particular, there are also other problems that you have to consider when you want to understand this problem. Besides the growing, is that if you want to understand this problem, you have to deal with different time scales. There are time scale of the order of the seconds, and that has to do with the mechanical relaxation, as you will see. There is scales that have to do of the order of minutes, that have to do with the gene expression, but you have to deal also with the scales that are at the scale of hours, that has to do with the cell cycle division. So there is a mix of cell scales that you have to consider. In particular, I'm going to focus on one particular time point that is going to cover 40 hours. Okay? These details are not very important for you so far. What is important is that besides the different mechanisms or the different stages that these two compartments of the DB organizer has to achieve, I'm going to focus on this particular region, in terms of time, that is the so-called the early and middle third instant of development. And I'm going to try to understand how this DB organizer can keep these cells segregated between the different compartments by studying how it can scale during 40 hours. And I'm going to understand this particular problem. In order to do that, you have to consider all the different things that are relevant in the system. One thing that is relevant in order to include in the system is the gene regulatory network that is active. I'm not going to enter here again into details, but there are some things that are going to be important when we want to implement that in the model. The important thing is that there is a quantity that will appear a lot here that is called notch. Notch is a receptor that is in the cells, and mostly is the more widespread receptor that is in eukaryotic cells. It's a receptor that becomes activated when a cell that is a neighboring cell, okay, has a ligand also on the cell surface, and this receptor and the ligand combine, and this creates what is called the activation of the notch. And this activation of the receptor produces other genes. In particular, one of the genes that is produced is this one that is called wingless, that is the morphogen that I was talking about. This is the quantity that is involved in providing this positional information to the cells. In previous work, actually, I was talking about this gene regulatory network some years ago, here, not here, but to you, to this audience, and we were talking about to try to understand the gene regulatory network that was involved in this process. I'm not going to talk about this today, but some details are going to be important. In particular, the genetic profile, that if you want to identify the cells that are composing, that are creating this organizer, these cells, when you look at them, you will see some pictures now, all those cells have this receptor activated. Okay? And the cells that are in the compartments but not in this organizer, they don't have that receptor activated. The way they keep this receptor activated, as I was saying, is because they are in cell contact with other cells that are providing those ligands. I will tell you how can we model that in an effective way without considering this particular method. This is part of this work that we were doing in the past in order to understand how this regulatory network is working, and this is the comparison between the simulations and in vivo experiments. This region here, this line, is what is called the DB organizer, and is in red because all those cells have the receptor activated. Forget about this region, because this is a Newton experiment when you do a particular experiment such that you can activate that receptor in an artificial way if you want. But it's important is that this region is the one that is called the organizer, that is separating the population that are here and there. What is important...
What is the scale?
The scale is normally 2, the width is 2 cell wide. 2, 3 cell wide.
But it grows to 1,000 times.
You will see how it's growing. Actually, the good thing is that while everything is scaling isotropically, the width of this region is always kept to 2 cells.
2 cells.
And those 2 cells are actually the boundary, the organizer, that is acting as a fence for separating the cells that are in the different compartments. Okay. Actually, what I would like to point about this particular the gene regulatory network is these are different ways to characterize that here you have this receptor activated, and those are different ways to characterize where are those receptors that are activating those ligands that are activating the receptor. Is that clear so far? As you will see, the receptors are here flanking those cells. That means that the receptor, I am in the organizer, and I'm taking the receptor from the cells that are surrounding me. Okay? This is important in the way that we will implement in an effective way this gene regulatory network. What it is important also is that here I told you, and I tricked you when I said this is between nearest neighbors. And actually that is mostly true, but it is known since very recently, actually at the end of 2010, that some of this receptor can be activated also by a mechanism that are called Philippodia, and that means that the cells are extending like some arms, and they are taking the receptor from cells that are not nearest neighbors, but they can be nearest neighbors and things like that. And we want to consider that also in the model. Okay? So this is one part that we have to consider. This fence is characterized by cells that are taking their genetic profiles but become activated with cells that are in the compartments. Okay? And those cells can also activate that receptor by not nearest neighbor, but next nearest neighbors by means of this mechanism. Okay. What other things do we need to consider? Since we are going to deal with things that are growing, okay, how these things are growing. And this is, I want to focus on the red curve, and the red curve is when you look at this tissue, okay, you have the apical part of the cells, the apical surface, and this is a region that characterizes how this apical surface is going to grow with time. So those cells are going to grow up to the moment that they divide. So how is this growing of the apical size? This is time, or what is the same, this is the progression of the cell cycle, and what you can see is that up to the middle of the cell cycle, the apical surface is not growing, it's steady. And starting at the middle of the cell cycle, it starts to grow more or less on a linear way, up to the moment where the cell area is more or less double the size of the cell area, and at the time it divides. Okay? This is the way the area is growing. Something like this. Not growing, start growing in a linear way, the division event. And we will have to consider that also. There are other things. I told you the things are divided, but how are they divided? One way to characterize the division orientation is by means of what is called the Hertwig rule. That is actually something that applies in many, many cells. How is and this is something actually very old, but many biologists have forgotten about it. It's from the 1900s or something like that. Suppose that you have a cell, an epithelial cell that is quite polygonal, and you characterize what is the angle that characterizes the longest axis. Okay? Something like that. And now, when it comes to the division event, you characterize the angle that characterizes actually the division by plotting a line that is connecting the nuclei of the two daughter cells. Okay? What you see is that there is a large correlation between these two quantities. Okay? There is some dispersion, okay, that can be more or less plus or minus 30 degrees. But what this is telling you is that the cells are going to divide mostly with some dispersion, but in a direction that is perpendicular to the longest axis of the sun. And this is the apical surface. Okay? This is the surface that I was looking at in the previous slide. So far so good? Yes. Okay. Now, when you look at the DB organizer that I was talking about, and you try to see, okay, what if I want to know what is the division angle in these cells, what do I find? I find the following. Either if you characterize what is called the mitotic spindle, that is this structure that is trying to segregate the DNA between the two daughter cells. If you characterize what is the direction of the mitotic spindle, and you compare the cells that are in the compartments, that are these bars, or the cells that are in the DB organizer, you see that the pattern of division is different. As you will see here, most of the cells are dividing in a more or less parallel way to the DB organizer. What this is telling me is that most of the cells that are in the DB organizer actually has the longest axis, according to the Hertwig rule, parallel to the DB organizer. If you do the experiment in a similar way, but instead of characterizing what is called the mitotic spindle, but the post-mitotic allocation of the nuclei of the daughter cells, because the mitotic spindle can actually fluctuate a lot, what you see is a very similar result. Most of the cells of the DB organizer are dividing parallel, well, perpendicular, but this orientation is more or less parallel to the DB axis, to the DB organizer. If you compare two cells that are in the compartment, that mostly do in every direction. So we have to understand also how this can happen in my system without imposing it. Okay? More things. Since we are going to deal with dynamical problems, something that is going to grow, I would like to understand why is there something different in these cells with respect to the cells that are in the compartments, and actually there is something that is different. Almost by the end of the development of this wing disc, there is a particular region that is called, acronyms are very useful, are very well spread in biology, but there is a code that is called the ZNZ, that is called the zone of non-proliferating cells, meaning that in the region actually where the DB organizer is, that region, the cells are not growing anymore. There is a particular time point where those cells stop dividing. Okay? And there are different experiments that you can do in order to test that. One common experiment that you can see in biology is what is called the BRDU absorption, this bromodioxyuridine. It's a is a particular molecular form that if a cell has the cell cycle active, okay, you can see that that particular quantity is absorbed by the cells. But if the cell cycle is not active, you see that that particular molecular species is not absorbed by cells. And when you look at that absorption, you see that there is differences between the cells that are in the compartments and the cells that characterize this DB organizer. This is by the end of the development, but actually the stopping of the cell cycle is not something that is sudden.
So which is the difference?
Okay.
What the difference to be?
In the figures or?
Yeah, in the figures.
Okay.
So there is a difference, I don't know.
Maybe it's very subtle, but here you see that this region is kind of dark.
This is cell in the organizer.
These are the cells in the organizer. If you want, is characterized here by the green, and the cells here are kind of gray. If you want, here are more red. So that means that there is a difference in the absorption of this quantity, the bromodioxybidine, in that region that is the compartment, or in that region that is the DB organizer. So the cell cycle length is different in the cells that belong to the organizer or in the cells that are in the compartments. And we want to understand that, or how it is actually playing any role in the stability of this structure. On top of that, there is something that is well known, that is the duration of the cell cycle, besides that it can be different in different regions. Within a particular region, like in the DB organizer or in the compartment, is not something that is deterministic. It's a quantity that is stochastic. The duration has a particular variability from cell to cell. So the tissue has to deal also with this stochasticity and duration of the cell cycle. Okay. And last but not least, some mechanical effects that you need to consider. Here in these experiments, what they have characterized are these are the different cells, and here you can see something, I'm going to highlight it a little bit, that is called a myosin cable. Actually, it's an actomyosin cable. What that means is that here, the cells are creating links that have some mechanical effects. Actomyosin is something that can create tension. It's like a cable if you want. And here is the DB organizer, and actually the cells that are set in the DB organizer, they have this link that is creating this actomyosin cable. So the mechanical effects have to play also an important role here.
This in the intercellular space?
Yes.
Side.
Yes.
Intercellular.
And actually there are many examples, not only in this particular case. Here is the actin and here is the myosin, but there are many examples in development. This is one of the most recent ones where these cables develop. And those cables have been always associated with keeping cells segregated from one part to the other part. So the mechanical effects, we have to consider those, and those have to be important. So those are all the biological components that we have to deal with. How can we do that? I'm going to present you the modeling approach that we have been using, finally, and this is the so-called Vertex model approach. If you are familiar with Frank Julick's works, this is kind of similar, but ours is better, I have to say. Ours is better. Okay. What is the Vertex, the basic principles of the Vertex model approach? This is an epithelial tissue. Actually, this epithelial tissue here, maybe you can distinguish like a cross. Maybe. This is the DB organizer, and this is the AP organizer. This is the system of reference from which these morphogens are infusing to provide information to others. Anyway, when you look at epithelial tissue, like this one, when Imaginal this, what you see is that the cells can be characterized by a very reduced set of points, because they have this polygonal-like shape. Okay, So the vertex approach actually uses this approximation for describing each of the cells by a reduced number of points that are those vertices that are giving this polygonal shape to the cells. Moreover, what you can see is that all these tissues, like in the case of the wind disc, they grow in bidimensional epithelium. Okay? And moreover, so you don't have cells beneath that are pressing you or something like that. It's a bidimensional problem. And besides of that, what you know also is that all these cells have what is called an apicobasal polarization, meaning that most of the actomyosin rings or all the mechanical parts that are important to the cell are in the apical part. And the rest of the cell is like a hanging sac, if you want. So the forces are doing in the apical part, and the rest is like a fluffy thing. Okay? So the mechanics actually is important in the apical part. And this is going to be important because in the vertex approach, if you combine all these things, what you consider is that this tissue can be understood as a two-dimensional network of points that are the vertices of the cells. In order to do that, what you do is, for this particular group of cells, you characterize each of the vertices, okay? And each of those vertices has energetic configurations that depends on the cells that are surrounding that particular, are selling that particular vertex. In particular, the energy functional that we have considered in this problem is this one, when you have different terms. The first one, and the sum in alpha is a subindex that runs over all the cells that are selling that particular vertex. Okay? So the first term here is an elastic term that has to do with the area of each of those cells that are selling this particular vertex. It's like an elastic term that is telling you that the cell will like to has a particular elasticity. The cell will like to have at a particular point of the cell cycle a given size of the area, of the apical area. The second term that you have here, maybe you can identify it, is what is called a line tension, okay, term. And this has to do, in biological terms, it has to do with the fact that some cells will like to have some affinity with neighboring cells. Okay? If the line tension parameter here is negative, that will mean between these two cells, that will mean that I will try to make that part of the membrane as large as possible. Because will decrease my energy. Okay? So it has to do in biological terms with the affinity between different cells that I may have. The third term has to do with what is called the cortical ring. Inside the cell there is what is called a cortical ring that is exerting some pressure, trying to keep as minimum as possible also in the apical part. Okay? And in the last term that we have considered is that, as you saw in the previous slices, you may have mechanical effects, but they don't have to be per se isotropical. I may have a piece of cable here, but not here. So you have to consider also anisotropy terms, such that the activity of the cortex may have to be different here than in other regions. This is the mechanical configuration that we are using. With this energy function, yes?
So the second and the third terms has opposite effects. So the second term would like to have a very long boundary, because you say that...
It depends. This can be positive or negative.
Okay, so it could also...
Yeah.
But the third term for sure wants to minimize the length of the border.
The perimeter. This is the perimeter. It will try to shrink as much as
It
possible.
will be like a curvature-driven thing.
It will try to squeeze the cell. But of course, this has to compete with elasticity and things like that. Yeah. And this term is similar to this one, but is anisotropic in the sense that you can consider this kind of shrinking effect differently in one side to the other.
And the number of points where there is intersections, so this number of nodes, this is kept constant, I guess, because it's
no,
this could change also.
No. I can tell you, the code is a nightmare. Okay? Developing this code is a nightmare. Because these cells are going to grow, they can increase the number of sizes, they can divide, new vertices are created, new cells, and things like that. I was going to talk about that also. This is the energy, okay? But this is something that if you implement that in a particular tissue, then everything will relax toward equilibrium and that's it. But we don't want that. We want a tissue that is growing, okay? The relaxation is achieved using, from the energy I can derive the force, and from the force I can neglect this term using the inertia terms can be negligible using the low Reynolds-Numel approximation in this particular system, and then I can derive what is the equation of motion of each of these vertices due to this energy, if you want, due to that force. Yes?
So I'm a bit confused by this sort of description because you're putting some physical arguments to the vertices. I mean, what is important is the cell, and then you're just going a step forward, and now you're describing some vertices that now you say that they have zero mass, and the vertices will have some friction there. And how do you? I mean, is it real or is it just an effective way that you have to describe all these new physical terms?
Okay, so I don't know if you realize about the first slide when I have the title. There was a sentence that is said, all models are wrong, but some of them are useful. This is wrong, as all models. Okay?
I'm not saying
but
it's wrong. It's just
no, it's wrong. I'm telling you, this is wrong, as all of our models are wrong, if you want to describe that. Nevertheless, it is useful in the sense that you can actually make a good approximation of how is the behavior on epithelial tissue. Okay, I am aware that you are considering the movement of these points that are characterizing the vertices using, as you say, a zero mass approximation. Yes, this is a topological point of the cell with no mass at all. It's a topological description. And I want to characterize the movement of that topological point by means of some energetic configuration that maybe will tell us something about reality. As I was saying, if you do that, you implement this, you have the tissue will relax to equilibrium. Very boring. We don't want that. We want to consider more things. Things that you want to consider are things that are known in biology, what is called tissue plasticity. Cells can interchange their neighbors. They are not fixed in point, as I was telling at the beginning about the balloon. It's not a continuum medium and every point will keep their position there. They can interchange their neighbors. One cell can be a neighbor of this and in the next step can be a neighbor of another cell. So one rule that you consider is what is called, and this is known in biology, the so-called T1 transition. So these two cells were neighbor, and these two cells were not neighbor. But given a particular point, they can change their neighbor, and now the cells that are neighbor are these ones, and those are not neighbor anymore. Neighbor, of course, they are sharing this, okay? But they create this, change this link. New vertices are created for the cells, and things like that. And this gives the tissue some plasticity in order to move the vertices, create new vertices. The shape of the cells are going to change, and things like that.
Although you have an equation for the movement of the vertices.
This one?
And that's nothing but a movement of the vertices, right? Of the vertices?
Those vertices are moving out of lattice. There is no lattice here. And it can be a particular configuration in the code when the size of that length of that cell wall is smaller than a particular threshold. this process is implemented. Okay?
So it does not appear naturally under this.
This one? No, because this is very tricky. This is very tricky. This is when you have like frustration in spin systems, the tissue cannot get 4 vertices, 4 edges in one vertex. This is something that is not an stable configuration actually. Okay? So you jump from here to there. This has been characterized in biology. Other transitions are you may have a cell that is going to die just due to the pressure or things like that, or due to an apoptotic process. That cell can disappear. These are reversible process. This is a reversible process. Everything implemented creates different topologies. How do you consider all the other things that we have been discussing before? I'm going to specify in the simulation a 2-cell wide at the beginning as the initial condition, that is going to be this organizer. You will see that it's going to be marked on red. And those cells will have the organizer character, if you want, but they can maintain the character if and only if the neighbor of the nearest neighbor have a compartment character. And I'm going to do that because, as I was telling at the beginning, for this cell to maintain this notch activity, it needs to suck from the neighbors that are not in the organizer the ligands. So it needs to be, for maintaining this of character, needs to be close to a cell that has a non-organizer character. Yes?
But then by hand you're just putting that this will have will be 2-cell wide all the time.
No. No, because this is going to grow. They can exchange, they can move. Nobody is actually, you will see how important are all these parameters in there. Okay, this is one thing. Other thing, I was telling you about how this area is going to change in time. And I was showing you this particular graph from the experimental values. And I was telling you that no growing, linear growing, division. What we are going to do in order to model that is that first we are going to consider that the duration of the cell cycle is going to be this variable for a particular cell, and we'll have 2 components. One component that is a deterministic duration of the cell cycle. Why? Because at least there is always, for all cells, a minimal duration of the cell cycle. Okay? And there is another component that is stochastic. And it's going to be a Poissonian statistics, and this is going to take into account the variability, the stochastic variability of the duration of the cell cycle. This gamma parameter is going to characterize the weight between the deterministic or the stochastic components in the cell cycle. If gamma is equal to 1, all the cell cycles have the same duration. If gamma is equal to 0, the cell cycle duration is totally stochastic. In our case, this parameter is 0.8. There is some variability that deals with the experimental data. Moreover, with this characterization, you can actually write what is known in the biological measurements, that is the average duration of the cell cycle and the dispersion. And with these 2 variables, you can characterize both gamma and the duration of the deterministic time. Once that for every cell, there is a clock that is taking into account the duration of the cell cycle with these components. Up to the duration of the cell cycle, I'm not going to implement any growth of the apical area, and starting at the middle of the duration of the cell cycle, that is going to increase linearly, more or less up to a situation where the area is double, and at this point I implement a division area.
You said that twice, but in the figure before it didn't double, it went up to 4 or 5 times.
No, well, because there are many. Okay.
Yeah, it went from 0.2 to 1.8.
Yeah, so there are different things here. here, this is the area, actually, the scale that you have to look at. Okay? And it goes, actually, it's not double, as you see, it's like from 40 more or less up to 75 or something like that. Okay? Like this one.
I'm gonna see the red one.
Okay, from here up to there. It's not actually when the size is double, it's less than that. We have taken into account that also, that is not exactly the double. That's why here, I said approximately twice, but it's less than twice. Okay? What about the Herwig rule that I was talking about before? What we do is, okay, now this cell has to divide. How can I implement the Herwig rule here? What I do is that I take a description of this cell as a collection of rods, okay, all these edges. From that, I compute the inertia tensor with respect to the cell center. And with the inertia tensor, I diagonalize that tensor and I can compute the principal axis of inertia. This is telling me that the longest axis will be around this line, the shortest. Okay? The longest axis is along the shortest axis of inertia. Once that I have characterized, okay, this is the longest axis, I have to implement this variability that can be plus or minus 30 degrees. Okay? So what I do is, once that I have specified that, I throw a coin, implementing this dispersion, I move a little bit, this inertia tensor, and then I do a cleavage of the cell. And new vertices will be created, of course. So, with all this thing, I implement that in the simulation. Ah, no, there is something more. I forgot. Yeah. Now, there is, I told you also that there is this thing that the cell cycle duration is different in the compartment sense or in the compartments or in the boundary. And there is a very simple argument that you can understand why. When you have a disk that is growing like this, the area of the disk is something like this, of course, and this is due to the number of cells that I have due to the average area that they have. But the number of cells, if they are growing exponentially, I get something like this, and I can relate that the radius is going to scale with the duration of the cell cycle, something like that. Okay. Now, I have a particular cell population that is organized that I know that in the experiment is growing in 1D, not in 2D. If I try to do the same scaling argument with something that is growing in one dimension, okay, I get something like the radius, in this case the length, scales with this other thing. If I want to make compatible something that is a disk that is growing and within a population that is growing in 1D, I come to the conclusion that the duration of the cell cycle for these cells have to be twice the duration of the cell cycle of the cells that are in the compartment. And this is something that we also implemented. Now, this is how the simulation looks like. So we have the cells that are growing, and this corresponds more or less to 40 hours of growing of the disk. And as you see, everything is nice in the sense that, okay, I have a cell population that is the organizer. They keep segregated. I will address, Ernesto, your question in a minute. They keep segregated the two cell population. There is not intermingling. Everything is fine. Okay. How do we know that this has some correspondence with the reality? We can explain what it is observed, but we can do some numbers also. And these are some snapshots, and this is a highlight of the cable, if you want. Okay? That I was talking about. Things that we can do to compare with experiments. We can characterize actually what is the angle of these links that are creating this cable, if you want, the difference between the cells that are setting the boundary, and I can measure what is the angle that is forming with respect to the DB axis. And we observe something like this. This is all those edges put in a polar plot. And what you saw when you do an histogram is that mostly there is a minus 30 plus 30 degrees. This is telling me that there is a kind of zigzag, okay, in this cable. And this has been observed and has to do actually with the hexagonal coordination that is achieved in the network, as you will see. Things that we can do also to compare with experiments is what is called the laser ablation experiment. This is something that is now muy de moda. And what they do,
Very trendy.
very fashion. So what they do is that they have this cell. Remember that most of the mechanical activities here in the apical part, and what they do is that they focus a laser in one of the edges of the cells. They kind of break the cell here, okay, and they measure what is the separation between these two vertices as a function of time. And this gives you information about how much tension was accumulated here. And they can compare the curves and go into the simulations and compare the things. This is something that Frank cannot do. Because the way they implement this modeling is not in continuous time and they cannot do this kind of experiment. Okay. This is a laser ablation experiment that we have done in silico. Okay? So here we cut this edge and we saw how the separation is growing versus time. And this is the kind of curves that you observe actually in the experiments. And something that they knew in the experiments is that because there is this cable, when they break a bone that is in the boundary, when there is this cable, or a bone that is not where is the cable, they see a lot of difference. Actually, they see a difference that is fourfold in the initial velocity here when the boundaries start to set.
When they do these experiments, what do they try to learn?
They try to learn things like that, when there is more tension, the characteristic of time scale of the relaxation that is telling you what is the scale of the mechanical relaxation that you have in a cell, things like that. And they can understand anisotropies, like in a particular cell, this size is not this size, equal to this size, and things like that. So when we do that, this is for cells, experiments, a lot of experiments about cell ablations from cells that are at the DB organizers, and this is when you do the same for cells of the compartments or edges that don't belong to the organizer. And the initial velocity of the expansion that are indicated with these two lines is a fourfold, like in this case of the experiments. Other things that you can do is that, okay, let's characterize what is the division with respect to the DB organizer. As I told you before that there was a different pattern of divisions. And this is what we obtained. In the compartment, the cells divide almost anisotropically in any direction, but due to the mechanical effects, we are not imposing this. Due to the mechanical effects in the model, we saw that the pattern of division is larger such that the cells are going to divide perpendicular to the DB organizer. More things that we can compare. We can compare actually what is the distribution of cell sizes, of cell sites, not sizes. So, because I have polygons of different number of vertices, these are the experiments, and this is the results of the simulations. Okay? So mostly what you have is an hexagonal coordination. Most of the cells would like to have 6 edges. We can do also other kind of measurements like what is the average size with respect to the average size of in all the tissue for a cell with n vertices. And this is the simulations and these are the experiments. Okay? Now that we have understand more of the parameters, other things that we can do is, okay, this grows in a very nice way, but it is actually robust. It can actually prevent the cell intermingling. So for doing that, we do an experiment that is very useful, and they do that in biology, is that they have a particular group of cells that are dividing on a larger space than the rest of the cells. Because of that difference, there is a particular region that is exerting a pressure, okay, over that region. Where here, actually, you can see that there is a little bend. And actually, what we can see with these experiments is that the tissue can resist the pressure that is implementing due to the growing. I am almost there. Other things that we can do is that what they do also in the experiments is that they can create what is called ectopic boundaries or ectopic organizer. I'm not going to tell you how, but no matter the initial shape that they give to these ectopic organizers, at times evolves, they keep circular, like trying to minimize the surface tension with the environment. And this is one experiment. What we do is we have this egg-shaped organizer, and we saw that as time evolves, it becomes circular. Okay? So we can compare the numbers, and we can also see that the system is working in the sense that it's robust. But what is the different contributions of all these different things that we have considered so far? What we can see is what happens if you remove actually the organizer. Are the cells actually intermingling? And actually, yes, they are intermingling. So the organizer is doing something because it's preventing these kind of things. Well,
considering that we're putting two things which force them to be essentially one-dimensional, which is that you say that they divide slower, two times slower, and then the fact that they want to have second neighbors which belong to the other class. I mean, these two things essentially force the thing to be a boundary.
No. You will see. So, it's doing the job so far. You will see. Perhaps not too much. Okay. Actually, this is the kind of things that they saw in the experiments. Not that much. They don't create like a finger or like instability or something. Okay? You can actually characterize how disordered is this region by doing this trick of how is the orientation of the different cell ages. And you see that actually it's very anisotropical, meaning that they have this wavy thing. Okay? What is the importance of the different terms? And you will see that it's not as simple as considering, okay, something that is linear and is two-dimensional. The mechanical effects are very important. This is one experiment when we have the same affinity between all the different cells. And this is not robust at all. So it's not as simple as Ernesto was saying, this is something that is growing with a different cell cycle duration and things like that. No. Actually, the measures that and the different mechanical effects that you have to consider in the model to get something that is growing in 2D was a pain in the ass getting the parameters. Because the different affinities between the different cells, as I showed you here, play a very important role for creating a robust organizer. This is one particular example of one region. Actually, what you get is that when the affinities are all the same, you don't get this zigzag organization in the boundary. Because something that mostly actually is very flat. What happens if you remove the cable? Yes?
Then all the parameters in the energy you fine-tune.
We have to fine-tune all those parameters in order to reproduce the experimental values that we have, that are the distribution and things like that. And we have also to deal with the thing that is stable and things like that. And we perform also a robustness analysis in terms of the parameter. So we don't keep, this is only working for this particular set. We also, once that we characterize the wild type, understood? The wild type set of parameters, we also make a robustness analysis in order to see how robust if the system has a particular variation of one of them.
And how many parameters do you have?
Well, actually we have the elasticity. There are like 6 parameters. Only. Yeah, so no that bad. Actually, one of the nice things of Frank is that by doing this comparison between simulation and experiments, they could understand what is the particular region of the parameters in the real tissue. We did something similar to that by comparing different experiments. Here, I don't have the cable, and you say, so the cable is not playing any role. So what do you need actually the cable for keeping the things segregated? Actually, I tricked you because this is not robust at all. When you look at the situation when there is no cable, there are many places where the width of the cell is reduced to one cell. Here there is one particular example. Here there is one particular example. Moreover, if you repeat with this experiment what I was telling you before, I put in here a group of cells that is divided faster than the other one, and it exerts a pressure, this breaks. So the cable is very important actually to prevent a robustness. And in the experiments, when they remove the cable, what they saw is that in one experiment, the thing is perfectly normal, like in this one, and in another experiment, this is totally broken. So what this is telling you is that the cable is not actually fundamental, but it's critical in order to give robustness to the mechanism. I put a random cleavage direction. I'm not going to implement the Herbig rule here. And as you will see, this is also very important. And this has nothing to do now with the mechanics. This is something that has to do with a particular criteria of the cells dividing and along a perpendicular direction to the longest axis. So this criteria is also very important because if those cells don't believe or don't follow the Herbig rule, then the cable is not robust anymore. What happens with the cell cycle differences? Now the cell cycles the cell do not divide as the cell cycle duration is not different. This is not working either, because now this creates, as I was telling you before, that the scaling is going to be different in this region, and moreover some cells here, because they do not have contact between a nearest cell or a nearest neighbor cell that is in the compartment, they lose this organized character. Yes?
So the cell cycle ratio cannot be determined experimentally? And is that confirmed the 2-to-1 ratio? Or?
Okay, this is an excellent question. They do know that they have to be differences. Okay? Why? Because they know, because of these experiments of the RDU absorption, that at the end actually those are not dividing. And they are not stopped like suddenly. There is some slowdown of the cell cycle. And there are different measures that confirm that. But your question about, well, let's go and measure that. They cannot do time-lapse microscopy in vivo of this group of cells. Now there are some groups that they are doing that, but they don't have dynamical information about this cells. So they cannot actually measure the actual duration of the cell cycle. The best that they can do is that they can take 100 flies, starting all of them at the same moment, and measure how many cells I have in this region, in this stage, and they see differences, but the quantification is not very precise. Mostly that was all that I want to tell you. Wow. Tell you about. So mostly from the methodological point of view, we have this wonderful modern toolbox for doing things with epithelial tissues. Here I present you a particular problem about the DB organizer, but we are doing other things, as you will see in a second. And from the conclusion of the biological and the physical meaning of this problem is that the organizer stability, what the biology know as the non-fence model, but model for biologists means other thing, as for physicists, depends on different things that we cannot quantify how important they are. The distinct mechanical properties like the adhesion or the polarized contractibility of this table that we have. A well-defined cleavage criterion that has to do with the Herbert rule, and also at the slowdown of the cell cycle. And we can put numbers of those things. There is a more philosophical, if you want, conclusion about that is the mechanics versus the signaling effects. When I was here 4 years ago, I was doing a lot of emphasis and was stressing how important is this gene regulatory network. And actually it's very important, but it's very important when you have to specify the population of these two cells. Without understanding this gene regulatory network, you cannot understand how much this receptor becomes activated. But once that receptor is activated, the important, actually, one of the conclusions that we have is that the mechanical effects are actually more important actually than the signaling, even, for maintaining the stability of the system. But you can try to combine the two things, and this is something that we are doing now. So these are future directions. There is a mechanism that is called the lateral inhibition model that is widespread also in developmental biology. That has to do actually with the formation of the eyes in insects and things like that. The lateral inhibition model means the following. You have this receptor notch again, and you have one of the ligands in a neighboring cell. And the lateral inhibition model works like when you have the receptor activated, this inhibits in the same cell to express more ligand for other cells. But in the cells where no receptor is activated, this actually promotes the creation of ligands. And this mechanism can be described by the so-called, this is a model that is very famous, that is called the Collier model. And with this model of the so-called the lateral inhibition, they can actually understand how is the formation of these kind of patterns, where you have Knox activation and cells that are surrounding when you have no Knox activation. Biologists also refer to this to the winner-takes-all model, because this cell becomes all the ligands of the surrounding cells, and she is very happy, and all these guys cannot activate the receptor. However, this pattern, if you want to understand the realistic behavior of the lateral inhibition, again you have to consider something that is growing. So things that we are doing are the following. We are doing modification of the Collier's model such that the receptor of the activation of the receptor depends actually on the length of the membrane that they are sharing. If they share a very, very tiny piece of membrane, they cannot activate a lot of receptor compared to this situation. So we weight this with the length of the membranes, and we implement that in a simulation in a tissue that is growing. And we compare actually what are the differences that we can obtain in this situation with respect to the static lattice, and compare also with the experiment. Mostly that was all. I have to thank the people. Frances and Jaume has been collaborator in this work. And Uriol is actually the one that has to take all the merit. He's a PhD student that will present the thesis. I'm very happy about that. The next month, probably. And he has been working with this gene regulatory network and the tissue dynamics and things like that. Thank you for your attention.
I haven't understood the rule by which one of these cells becomes the boundary, or the rule was that it was in contact with only with one which is in the compartment, and also either this or next in the label. What was the rule? By one, in the first simulation you showed most of the boundary was made of two cells, and there was some passing which there were three. So I don't understand exactly the first one. No, before that, for the first one.
Before. Later?
No, before that.
Before. You tell me stuff.
Before that. It was
Here?
the first simulation.
Simulation?
Yeah, the first simulation.
The first simulation, okay. First simulation is here.
It's behind that.
It's behind.
So what's the rule why some of the cells are red? Sometimes you see two lines of cells, sometimes you see three.
No, there are two in all cases.
No, to the right is three.
Well, there is three.
So why? And this is also the question by Ernesto.
Okay.
So what's the rule by which they are?
They are red because their nearest neighbor or the next nearest neighbor is a white cell.
And then why do you have a three line of? So
why don't you get that?
Yeah.
I don't know. mostly because they want to organize in a two-cell stripe because of the mechanical effects. The cell affinity and things like that it has a very important role for keeping that to a two-cell wire. As I was telling you before, if you do something okay. If you do a mutant, in the biological meaning that, okay, I have here the cell duration is different, everything is as in the wild type situation, the perfect and nice one, but I just removed one thing here, is the cell affinity is the same all over. There is not a special affinity for a red cell to be with a white cell or a white cell with a red cell. All of them have the same affinity to be with each other. The line tension parameter is the same. In those situations, what you see is that here you get that there is a wide spread of the boundary also. So the mechanical effects have to do also a lot with this kind of effects, like here in this one or here in this situation. I am answering.
How do you count the parameters? Because I see many parameters in your
5.
I count at least 8. Just, just looking at the formulas. Can you go back to this?
There are
At
6.
least, because I had at least.
As far as I remember, there were 6.
Go to the energy.
Okay, it's going to be slow, but eventually it will appear. Okay.
So K alpha is equal for all alpha, or are this constant or percent?
This is a parameter that is related with the Young modulus.
But it's K, so alpha is not
Yeah.
depends on alpha.
Pardon?
Depends on alpha.
Yeah.
Depends on the. So you have many.
But what it is known, okay. This is a general term for the energy functionality one. But in our simulations, if K is going to be different, okay, what you expect is that when they characterize the cell size, they can see difference between cells that are in the compartments or in different regions or things like that. But actually what they see is that this is very well characterized. So we are considering that the lasting constant of all these cells is going to be equal. Okay?
So K alpha is only
one parameter.
The lambdas.
Now,
the areas. A0.
A0 is something that you can measure. You don't have to
But
tune
it's a
them. It's a 10. It's a constant. It's 10 microns squares. Okay?
1.5. 2.
So 1. There is just one. The parameters that I have to fit, not parameters that I know from the experiment. Okay?
Lambda.
Now, we have these parameters that have to do with the cell adhesion. Okay? And actually, there are different cell adhesion terms. There are the adhesion between a white cell and a white cell. This is now the second parameter. Red cell and red cell. And white and Well, the other combination. So we have 4 parameters so far. We have the contractibility, that is the same for all cells, 5. And now we have the anisotropic term, that is actually only relevant in the cells that are only for the vertices that where there is a cable. For the rest, it's 0, so I don't have this term. So 6.
Plus the gamma, plus the deterministic time.
Okay, the deterministic, the damping term can also be inferred from the experiment by comparing what is the difference of what you know from the experiments is that the realization scale of the mechanic scale compared to the cell cycle duration is 100 times-fold larger. And from that comparison between the duration of the cell cycle, that is something that you know from the experiments, and the realization of the mechanics, you can derive what is the value of gamma. So this is something that I don't have to fit. I can.
No, you have those, some of them you can extract from the experiment.
Yes.
You still have 9 so far.
No, 6.
6 plus the gamma plus Td.
Okay.
Td plus you have the shape of the curve in which the area grows.
Yes.
It goes from 1 to double. This doubles another parameter.
Well, this double actually, well, if you want, it's a parameter, but it's something that I know from the
Okay,
experiment.
now so you have many parameters, at least 10. Some of them you can extract from the experiment in a straightforward way.
Yeah. So the only ones that I don't are these 6. All the other ones that appears are something that I can extract from the experiments. Yeah.
Any other questions?
And believe me, it's not trivial at all. It's no. I'm telling you this because we have to think a lot about something that many times is counterintuitive. For instance, you may think that what it will be the better for maintaining an organizer is that the affinity between cells, is the larger as possible. Okay? Meaning, so this is like the cable, this is cells that are here in the organizer. So maybe you think a trivial solution is that, if this is very negative, they will try to align in this direction because they have a lot of affinity and things like that. And moreover, the largest angle for having this experimental fact that they are going to divide along this direction is going to be satisfied. However, if you do that, the system doesn't work and the boundary breaks. And it has to do also because if you do that, you reduce the affinity between these two cells that are in this line. And so actually in the model, the line tension from this side is positive. They will try to reduce as much as possible this length. And when doing that, you have that the cells elongate in this direction. It's kind of counterintuitive.
Javier will be here until tomorrow afternoon. If you have time to talk with him.